Okay, I'm going to do a couple of examples from page 219. On these first two examples, if you look on that page, we are using the first derivative test to determine the local extreme values, and we have to identify any absolute extrema. It does say to support your answers graphically. I'm going to leave that part up to you. You can use your graphing calculator just to show that this actually is true. So we're going to start by finding the derivative. So here we get y prime equals negative 6x squared plus 12x. So that's the first step. Then remember we have to set the derivative equal to 0 and also find where the derivative is undefined. Well, since it's a polynomial function, there will be no places where the derivative is undefined. But as far as when the derivative is 0, we have negative 6x squared plus 12x equals 0. So we're going to factor out. I'm going to factor out a negative 6x. And if I do, I get x minus 2. So then I have x equals 0 or x equals 2. So these are my critical values. Also remember these would be considered stationary points. So the next thing I'm going to do is create a number line or a sign chart. I'm going to use my two critical points. Remember this is a sign chart for y prime and the derivative values are 0. So then we need to determine, using the first derivative test, we need to know if it's positive or negative on each side of our critical points. So if I use a point in between, if I substitute in a 1, and remember we're plugging that into the derivative, we don't care the value, we only care if it's a positive or negative. So if I substitute in a 1, then I'm going to have a negative 6 and a positive 12. So I end up getting a positive value. Then the next thing I want to do is substitute in, say, a negative 1, something to the left of 0. So if I plug in a negative 1 here and square it, I'm going to get a positive. So I'm going to have a negative here, and I'm going to have a negative here. So when I add those together, I know it's negative. Again, I don't care about the value. Now I'm going to use a 3, something larger than 2. So if I do that, I just have to determine which is going to be greater. I'm going to have a higher negative value than I am positive. So this over here, that sum will be negative. So what that tells me by the first derivative test is because at 0 it's going from, the derivative goes from negative to positive, that indicates that we have a local min when x equals 0, since y prime goes from negative to positive. And you do need to have that justification on your paper. Then we also will have a local max when x equals 2, since y prime goes from positive to negative. Now, that's not what the values are. If I said, what is the local min, you have to take that value and substitute it back into your original function. So the actual minimum value, which we needed to plug in a 0 up here, so our min, if you plug a 0 into your original function, you'll get a negative 3. So we have a minimum of 0, negative 3, and we have a maximum of 2, and if you substitute a 2 in there, let's see, we get negative 16 plus 24 minus 3, so we should get 5. Hopefully I did that right. Okay, so that would be how you would do that problem. Let's look at number 4. This one's a little bit more complicated as far as the derivative. So we start by finding the derivative. And you're going to need to use the product rule. So if I consider the x as u, so u prime is 1, and v prime, remember the derivative of e to the 1 over x is e to the 1 over x, times the derivative of 1 over x. Remember, this is the same as x to the minus 1, so it would be negative x to the minus 2. So we have a negative e to the 1 over x over x squared. Okay, so then for y prime, we get u prime v, so we're going to have 1 times e to the 1 over x plus uv prime, so we have x times negative e to the 1 over x squared. Can do a little canceling here because this x squared, one of the x's here, cancels that. So we get e to the 1 over x minus e to the 1 over x over x. Now remember when I talked about how if you have a fraction, a sum or a difference, you really want to put this together into one fraction. So I'm going to need to find a common denominator. So I end up with x times e to the 1 over x minus e to the 1 over x all over x. And the reason I want to do this is because remember we need to find where is the derivative 0 and where is the derivative undefined. Well, if we have it as a rational function, we set the numerator equal to 0 to find where the derivative is 0, and we set the denominator equal to 0 to find where it's undefined. So that's what we want to do. So y prime equal to 0. We take, I'm going to factor out at e to the 1 over x, and we'll get e minus 1. I'm sorry, x minus 1. Okay, so that means e to the 1 over x equals 0, which, think about it, this is a exponential function, and it will never be 0. So this part, never 0. So we end up with just x minus 1 equals 0, or x equals 1. This is a critical point. I also need to look at when y prime is undefined. Well, y prime is undefined when x is 0, but if you look back at the original function, x can't be 0 because it's not included in the domain because we can't have e to the 1 over 0. So I don't have to worry about when y prime is undefined. It won't be a value. It does happen when x equals 0, but it can't be a max or a min because the function is not defined. So I'm ready to take a look at what's happening then. I'm going to mark a 1. And this is y prime, so that's a 0 value. I'm also going to mark the 0, and I'm going to put y undefined, just to remind me. Because when I substitute values on either side, one thing I have to be careful about is not passing over any critical points when you are testing values. So I can't test, if I want to test something to the left of 1, I can't test a negative. I need to stay between 0 and 1. So I'm going to start by substituting in something larger than 1, and if I do, remember we're going back up to our derivative, so I'm going to use the factored form because it will be easier. If I substitute in a 1, I'm only looking for positives or negatives, so something larger than 1, this is always positive, so I'm not going to worry about that. But say I plug in a 2, 2 minus 1 obviously is positive, and then my denominator will also be positive, so I'm going to have a positive result here. Now I'm going to choose a half. Don't have to worry about the 1 over x, e to the 1 over x, that's always positive. A half minus 1 is negative, and then a half plugged in here is positive, so I'm going to end up with a negative over positive, which is negative. Now if you substitute in a negative to see what's happening on the other side of this value, because x could be negative in the function or the derivative, it just can't be 0. If you do plug in a negative value, you're going to find that your let's see what well, I'm going to come back to that later, or maybe we will in class, because I want to talk about how we know that this can't be a max or a min because it's not defined in the function. So really this is our only critical point we have to worry about. So if we, based on the first derivative test, since the derivative goes from negative to positive, that tells us that we have a local min. So we have a local min at, and let's go ahead and find what that value would be. If you plug a 1 into the original function to find out what the minimum value would be, we're going to have y equals 1 times e to the 1 over 1, or e to the first. So we just get e. So we're going to have a local min at the point 1, e. don't forget your reason, since y prime goes from negative to positive. All right? And that is how you will do that first section when you are doing problems 1, 3, and 5.